sir. You had a question. Yes, if p-value is greater than 5%, you will say that you will reject the alternate hypothesis. If p-value is less than 5%, you will say that you are not able to reject the alternate. Yes, anything else? Any other questions?
Sir, I have a question.
Sure, tell me.
Sir, once you set up.
Can you speak a bit louder if possible?
Yeah, you can hear me now, sir.
Yes.
Sir, when you set up a null hypothesis like something equal to this, right? Then in that case, if my alternate is equal to my alternate is greater than or less than, so it is considered as a one tail test, right, sir? If my alternate is not is equal to, it is going to be like a two tail test, correct, sir?
Right.
Okay.
So the usual framework of a null hypothesis is you will write H0 and then H0 will look something like this. H0 basically will say something is equal to another thing, right?
Yeah.
This is the format of null hypothesis. Now this something can be a parameter. This something can also be a parameter. By parameter, I mean either mean or standard deviation. This something can be a value as well, right? But the format of null hypothesis is it is always some parameter is equal to either another parameter or a value. There will be always a equal to sign. If the alternate hypothesis talks about greater than sign, then it will be a right tail test. If it talks about a less than sign, it will be a left tail test. If it talks about a not equal to sign, it is a two-tailed test.
And sir, type 1 and type 2 error is similar to this?
No, we have not talked about that. We'll come to that.
Okay, sir.
Okay. Sir, I have a few questions from the earlier classes.
Yeah. Yeah, tell me. Hello.
I think I'm having some problem. Just hold on, sir.
Okay, so we will continue and maybe take up the questions later on. Anybody else has any question?
Sir,
sorry?
Sir, when I was going through on the book and internet about the p-value, so as you said, the only we have to understand that if p-value is less than 0.05, so in that case we accept null.
No.
We reject null. Sorry. If it is greater than that,
p-value is greater than 5%, you will reject the alternate. If p-value is less than equal to 5%, you will not reject the alternate.
Okay, we are only talking about alternate. We can't say any statement about the null hypothesis, right, sir?
No. Technically, you can't. But I mean, logically thinking, if you reject the alternate, what else remains? Null, right?
So, sir, it is saying area outside the curve. So, what is mean by this? Means what you are saying, like something beyond certain limit. Area outside the curve means in the p-value, I found out one line in the book written like area outside the curve.
Yeah, we were calculating area to the right or to the left, right? That's the p-value. So it's area outside that particular line.
Okay. Thank you.
Sir, I have the questions.
Yeah.
Sir, in the PDF, basic statistics, the slides, in slide 3, in this multimodal data, it says the data is mode 27. So is that how we represent it, sir?
Sorry, which page you
slide 3. Slide 3.
Slide
Page 3. Let's say page 3. Page 3.
Got it. Okay. Page 2, page 3. This is the page, right?
Yes, sir.
Or this is the page.
Below. I think slide 5 or 6 it must be.
Yeah.
Below the slide, sir. Yes. In this graph, there are 3 values for 27. So it's a multimodal data.
Correct. That's what we discussed yesterday. Somebody had asked this question, right? Was it this batch? Somebody had asked this question that what if there were multiple values that had the highest frequency? There are 2 ways to go about it. One way is often what people do is people take their average as the mode. So it will come out somewhere in the middle. The second way to do it is you will say that we do not have one single mode, but rather we have multiple modes. So all of these values will now become the mode. So for example, in this distribution, what are the modes? Modes will be minus 5, minus 1, and 5. All of these 3 are modes. This is a multimodal distribution.
We represent it as multimodal data with modes minus 5, minus 1, and 5. Is that how we represent it?
Yes.
So on page 5.
Page 5, which is this one, right? Oh, this is 3. Sorry. Yeah, page 5. Yeah, tell me.
Page 5, sir. There is a line which says dispersion refers to the spread of variability in the data. It determines how spread out are the scores around the mean.
Correct.
So should it be mean or should it be mode?
Okay, now we discussed dispersion, right? What is the most common measure of dispersion?
The most common is mean, but
Most
the
common
mode
is
mean.
Standard deviation.
No, most common measure of dispersion is standard deviation.
Yeah, standard deviation. That is right. Yeah.
So in the standard deviation formula, you calculate the spread with respect to what? Mean or mode?
Mean.
So this answers your question, right? So it's the variability about mean.
Yeah, but whenever we represent it, we always take it as the highest point and then left and right.
Not really. I mean, in most of the cases, we show a bell curve, right? In that bell curve, the mean is actually equal to mode. We are taking it around mean, but inadvertently it's also around mode because mode is also equal to mean. So that's an inadvertent coincidence that happens, right?
Okay.
But we should always take it around mean, not mode.
Okay, so technically it's around mean, but
Exactly.
just
But
because
if
we
mean
are
is
looking
equal
at
to
a
mode, then then it also becomes around mode. Yeah.
Okay, sir. On page 11.
Page 11, 5, 6, 7.
Sorry, I have a couple of questions.
No, it's actually good. This is the first time somebody has actually gone through the pages. Yes. I mean, we have not covered this, by the way. I was about to cover this, but yeah. Do you have any question with respect to sampling?
Yeah, that is, I think it's in the next slide, if I'm not wrong.
We have not covered sampling, by the way. So we will cover this.
Okay. It's a very generic line, actually. I think it's in the CLT only because there are 2 slides in the same page. CLT.
Okay, CLT we have covered. Yeah, tell me, what is your question?
So there is a line which says statisticians know that repeated samples from the same population give different sample means.
Yes.
So what do you mean by that? Because
say for example, let's consider the population of India, right? And let's say I take a sample. So what I do is I go out right now and get the age data on first 5 people that I find. It is a sample from the population of India.
It's true.
Okay. Now let's say you also go out and get age of 5 people that you find. That is also a sample.
Yes.
Will if I calculate the average age based on my sample, and if you calculate average age based on your sample, it might be that our means are not equal, right?
Understood, sir. Because the
That's what
population is a bigger universe and the
exactly,
sample
and
is
we
a
are
smaller,
looking at smaller samples. Yes.
so it can be anything. Okay,
Exactly.
that is understandable. Okay, sir. On page 17,
17. Okay.
that example 1.
16, 17. Yeah. Okay.
The example 1. Now, sir, in this question, I think we did it in the class as well.
Yeah.
But in this question, it says that the normal distribution with a mean of 92 and a standard deviation of 3.1. Then it goes and says that we collected samples from 50 service stations and obtained the mean of 93.6.
Right.
But while on the other slide, when we did the calculations,
Mm-hmm.
we are considering the population standard deviation and not the sample standard deviation.
Yeah, we were considering population standard deviation, right? Because here it says the population standard deviation is 3.1.
Should we not calculate the standard deviation if we are given the data tomorrow as a data analyst?
Mm-hmm.
We should be considering the population standard deviation, or should we be considering the
So
sample?
remember we were using what theory to test this hypothesis?
The CLT.
CLT, right? Now, if you go back to the statement of CLT, the CLT statement does not talk about sample standard deviation. It talks about population standard deviation, right? So to apply CLT, we need to know the population standard deviation.
So that means that we need to know the whole data of the population in that case.
Not really, not really. I mean, see, population standard deviation can be obtained in a number of ways actually. Say for example, if I want to know the standard deviation of age in India, what I can do is I can look at some old census report and get the data. Now, what would have happened is, although the average might have changed, the standard deviation is something which does not change over time. You understand, the whole population, if I say calculate the standard deviation of population in India today, after 1 year, what will happen is the mean will move by 1 unit because the whole population has shifted by 1 year. But the standard deviation will still remain the same. So standard deviation is something which seldom changes. So you can get it from different sources if you want, right? Whereas the mean is something which is very volatile. So standard deviation of the population is sometimes known, but having said that, there are other ways to test hypothesis if it is not known. You will not be able to use the CLT, but there are other ways to do it.
But still, we need the whole population data to calculate the standard deviation.
If you do not know the population standard deviation, you cannot use CLT, then you will have to use some other theorem. But there are other ways to do it as well.
Okay, so CLT is generally used for data which is repetitive, which has analysis done.
CLT is used when you know the population standard deviation. When you do not know the population standard deviation, you will use something else.
Okay.
Yeah.
Sir, on page 19.
19. See, one second. I will not go into this because this will do it in class.
I understand, but this is a T-test. I'm not talking about that. I just want you to talk about significance level. I think the earlier question was also for that. The significance level says that alpha is 0.1.
Yeah,
as
we will
want
always take at 5%.
Yeah, so if you added that 5 on both sides and then got alpha, right?
Sorry, we will always take alpha as 5%.
Okay, but in this question, it says that we want to be liberal rather than conservative.
Yeah, I will explain what we mean by that when we come to this.
Okay. Sir, another question that I had from the lecture.
Your question is on this statement, right?
That is right, sir. When do we come to this? When do we consider this?
I'll consider. I'll explain this when we come here.
Right, sir. So another one, in the class lectures that we did an example we did an example in which uh, we took samples of 20 people. It's
Okay.
not in the slides.
Yeah.
We took a sample of 20 people, 10 samples, and then we did the frequency distribution, the probability distribution for that.
Correct.
And then we were trying to say that it's a normal distribution if you get that.
Correct.
I just want to know, when we are collecting data for 10 days and we are collecting 20 data points every day,
Correct.
why are we not considering 200 samples and considering only 10 samples?
You will, but the reason I use that example, I wanted to explain the central limit theorem theory to you. That's why I made it 20 different samples or 10 different samples, right? Because I wanted you to understand CLT. But in practice, when you collect samples, you will probably accumulate them together and treat them as one single sample. The reason I made them different samples, because I wanted you guys to understand that if I plot a frequency distribution, I'll get a bell curve. If I combine them, I cannot have then a frequency distribution, right? I'll have a single mean. You understand the problem, right?
I understood.
The only reason that I treated them as different samples is because I wanted you guys to understand the concept of frequency distribution. If I combine all of it, I'll get one single mean. Then there's no frequency distribution, right? So that's the reason. I mean, practically, you will probably combine all the 10 samples.
Okay, sir.
Yes.
Another thing, sir, I need some help in CLT. So can I take some extra time from you, or you can? If I'm not sure if everybody has understood it, we can run through CLT again, or I can take some extra time from you sometime.
Yes, sir. Can you please repeat the CLT again?
Okay, I will explain the CLT again, but before that, I need to do something else as well. Any other question before we start?
Sir, you talk about the concept called standard error, right? So because we are taking sample from the population, right? So can I say like standard error is a difference between population mean and minus sample mean?
No, standard error is population standard deviation divided by square root of sample size.
Okay, so means this is not like a difference population mean minus sample mean. This is not a standard error.
Standard error, it is clearly defined as the ratio between population standard deviation divided by square root of the sample size that you have taken.
Yeah, okay.
It is not an error per se, right? It's just name that has been given to this quantity.
Because in central limit theorem, I read out somewhere that larger the sample size, it means we are closer to the population, right? So closer to the population means that we are representing the like true population in that case, right? So we are going to get the like a less mean difference in population and sample. So low chance of error. I found someone from internet, but I'm not sure this is correct or not, what I'm saying.
No, it's not. I'll explain. I mean, I understand what you have read, but I'll explain it.
Sure.
Anything else? How much sample? Depends on what amount of confidence you want. Last day we did it, right? We talked about. So it depends on how much confidence you want. So I mean, what? So now, how much data you want? This is not a. There is no straight answer to it, right? The straight answer is as much as you can have. That's the straight answer. But if you want to figure out, say for example, I want to do a hypothesis test, and I want to be like 99% sure of the findings, right? So then what I can do is I can use the central limit theorem to figure out how much sample should I take if I want to be 99% sure. Right? Okay. Anything else? Okay. So now I'll repeat central limit theorem, but before that, there are a couple of things that I skipped. I skipped because they were like simple enough. So I skipped, but anyway, we'll go over it, right? We'll go over it from the beginning. Typically in analysis, there are two kinds of data: categorical, quantitative. Categorical means things which are not numbers, like hair color, eye color, gender, etc., name, address. Anything which is not number, is treated as categorical. Anything that is number is quantitative. Quantitative is of two types, discrete, continuous. Discrete are those types of numerical variable that can only take integral values. And continuous are those type of quantitative variable that can take values in decimal points. Example of discrete, number of people standing outside your house can never be in fraction, right? Number of times you go to a particular shop cannot be a fraction, right? Examples of continuous, age, height, weight, income, these can all be in fractions. Make sense? Okay, this is simple, right? Just you need to go over this. Then comes the types of statistics, right? Statistics typically is of two types. Now we are not talking about machine learning here. We are talking about pure theoretical statistics. Theoretical statistics is of two types, descriptive, inferential. Descriptive basically deals with describing the data that you have. Describing the data is what we had done in the ice cream parlor example, right? We had described the data by doing what? By calculating central tendency dispersion. Also, we tried describing the data by looking at the frequency distribution and the probability distribution. There, we were only describing the data that we had, right? We did not do anything else, right? We were just describing the data. Inferential, on the other hand, talks about looking at a small portion of the population and inferring on the whole population. That's what we are doing in estimation and hypothesis testing, right? We are looking at a small portion of the population and we are trying to draw insights on the whole population, right? Say for example, finding the average age of Indian male in India. You look at a small portion and try to find the average for the whole population, right? That is inferential statistics. Clear? Example of descriptive is whatever data you have, calculate mean, median, mode, maximum, minimum, range. Any calculation that you do typically to describe that data will be descriptive, right? Any calculation that you do to draw inference on a larger population will be inferential. Make sense? Okay, next. Measures of central tendency. I guess we have gone through this, right? Mean, median, mode. Now, what are the advantages and disadvantages? Mean, it's easiest to calculate, easiest to interpret, right? All of us are familiar. So if you go to a business person, the first thing that the easiest thing to explain to him is the mean, right? A disadvantage, mean is influenced a lot by very large or very small values. Say for example, if there was one person sitting in this room whose age is like 95, the average age of this room will get skewed towards higher value. Similarly, if there is a baby inside the room, the average age will be skewed down to a lower value. Understand? Mean is affected by large values and as well as small values. Median. Median advantages, it is not affected by large or small values. It's the middle value, right? So even if a very large value comes in or a very small value comes in, median more or less remains constant. The disadvantage is it is very complicated to communicate. The reason being, you'll have to explain what you mean by the middle value, right? You have to explain the whole process of calculation. People do not typically are familiar with median. Mode. Mode is again not affected by outliers, right? That's an advantage. The disadvantage is there is no particular use of mode, right? No statistical theory is based on mode. So, I mean, in the long run, the only use of mode is to calculate central tendency for categorical variables. Because for categorical variables, you cannot calculate mean, you cannot calculate median. You understand, right? There cannot be a mean or median for hair color, but there can be a mode. Make sense? So mean, median, mode are three measures. Each of them have their advantages and disadvantages. Okay. Now, we talked about this histogram. This is basically a way to show the population distribution. If you now divide each of these frequencies by the total value, you get probability distribution. The shape will remain the same. It's just that the scale will be between 0 and 1. Okay. Okay. Then we also have talked about coefficient of variation, right? Okay. Now, the next concept is dispersion. In dispersion, we talked about range, we talked about standard deviation, and we talked about coefficient of variance, right? Apart from that, there are few more other measures which are there, which we will discuss as and when we use them, right? But the typical measures which are the most used measure of dispersion is this, right? If you are just understand this, you will be fine. Okay. We'll come to it when we use it, right? Okay.
Deviation?
Sorry, what?
What is mean deviation?
Yeah, mean deviation is the average value of the absolute difference between xi and x bar. This is mean deviation.
Okay.
Yeah. So when we calculated standard deviation, we discussed that there were two ways to remove the signs, right? One was squaring, second was taking an absolute value. Remember in the calculation, instead of taking a square, if you would have taken the absolute value and taken an average, you would have got a mean deviation. Right? If you square it, take an average, take a square root, you get standard deviation. Okay. Again, having said that, the only thing that you need to understand is this. Anything else is not required. One more concept which is required somewhat is percentiles. We will talk about percentiles when we use it. Right now, you don't need to worry about that. Next, common measures of dispersion. It talks about standard deviation. We need to go through this. We talked about coefficient of variation. All of you are clear with this? Okay. Then we talked about, I'll come to outliers later on. We talked about normal distribution, and we talked about the probabilities between mu plus minus sigma, plus minus 2 sigma, and plus minus 3 sigma. Okay. Then we talked about what is standard normal distribution, right? Then we talked about how can you standardize a normal distribution by subtracting the mean and dividing it by the standard deviation. Now remember, this transformation will convert any distribution to standard normal, provided that distribution is already normal. You cannot convert a binomial or any other distribution to a normal distribution using this. What you can do is, if your variable is already normally distributed with some mean and some standard deviation, you can convert that variable to a standard normal. So this is non-standard normal to standard normal. This does not convert any distribution to standard normal. Okay, so this is a practice problem, which is fine. Then we talked about the concept of population and sample. We talked about point and interval estimation. Make sense? Okay. Yes. Now, the next concept which we did not talk about is what are the common ways of collecting samples. The common ways of collecting samples are typically three, right? The most basic way of collecting a sample is simple random sample. Simple random sample is going out collecting a random entity, right? Just go out of this room, collect the first person that you get. That is simple random sampling, taking random values. Simple random sampling can be of two types. Simple random sampling can be of two types. The two types are simple random sampling with replacement and simple random sampling without replacement. SRSWR and SRSWOR, right? You need to understand the difference between these two. Let's understand this by taking an example. So let's say you have in a box, you have 4 small balls. Each of the, basically you have the pool table balls. Each of them have different numbers on them, right? The balls have numbers from 1 to 10, let's say, right? These 10 balls are there in a box. When I say simple random sampling with replacement, if I ask you to get me a sample, so get me a sample of size 4 using SRSWR. When I say something like this, what you should do is go to that box, randomly select one ball, right? Randomly select one ball and note down the number on it, right? Let's say you select ball number 5. You noted down the number. Then what you do is you put back the ball in the box. So you are replacing the ball, right? That's why this is called simple random sampling with replacement, right? So after every draw, you put back that value or that observation or that ball in this case into that population, right? So if you do that, what might happen is the next time that you draw, you might again get 5, right? So simple random sampling with replacement may result in a sample that has duplicate values. That is a disadvantage, right? The advantage is I can generate an infinite size of sample from a very small population. So I have 10 balls here, right? But I can keep on repeating this process for an infinite number of times, right? So this is an advantage, right? Disadvantage is duplicate. Advantage is you can generate samples of any size. Clear? Okay. Now, simple random sampling without replacement. So if I say, get me a sample of size 4 using SRSWOR, what you will do is you will go to the box, collect one ball, let's say it's ball number 6. After you have noted down the number, you do not put that ball back into the box. So what happens is every time you get a new observation. The advantage is you will never have duplicates. The disadvantage is the sample size is limited to the population size. Make sense? Okay. So this is simple random sampling. Simple random sampling are of two types, SRSWR, SRSWOR. Okay. Now, the next type of sampling is known as stratified sampling. What is stratified sampling? Stratified sampling is where you split the population basis some sort of variable before you start sampling. So what do I mean by that? Let's say out of these 10 balls, some of the balls are red colored, some of the balls are black colored, right? Let's say 1, 2, 3, 4, 5 are red, 6, 7, 8, 9, 10 are black. So if I am doing stratified sampling and I define the strata basis the color of the ball, what I will first do is I'll divide the population first into two parts basis their color. Now I have basically two populations. Now if I ask you, get me a sample of size 4 using stratified sampling based on color, what you will do is you will go to the sample of black balls and collect 2 balls either using SRSWR or SRSWOR. Similarly, go to the population of red balls and collect 2 balls using SRSWR or SRSWOR. Make sense?
Sir, what is the main difference between SRSWR and SRSWOR?
The main difference is in SRSWR, there is a possibility of getting the same observation multiple times. In SRSWOR, that is not possible.
Okay, because in SRSWOR, whatever sample we are getting, we keep it aside and we
Exactly.
collect the sample from the remaining one.
Exactly.
Okay.
Yeah. So you understand stratified, right? So you basically split the population into stratas. Stratas means nothing but subdivisions, and you select observations from each of these stratas.
The stratas could have a different number of balls, right?
Yeah. So now let's say in this particular case, both these stratas has equal number of observations, right? Now, what if 8 of these balls were black and 2 of them were red, right? In this case, you will select equal proportions. Say, for example, right now 80% of the population is black, 20% is red. Make sense? So if I want to select 4 balls, what is 80% of 4? Around 3, right? So what I'll do is I'll select 3 out of this black proportion and 1 out of this, so that my sample maintains the ratio that is there in the population. Yes, sample of size 4 means get me 4 balls, or the numbers from the balls basically. Okay. Okay, now, so this is what we have on simple random sampling and stratified sampling. Now remember, stratified sampling is also of 2 types based on whether you use SRSWR or SRSWOR. After you have created the strata, you can use with replacement as well as without replacement, right? So based on that, this can also be of 2 types. Stratified sampling with replacement, stratified sampling without replacement.
There could be 3 number of stratas, more than 2 also.
Yeah, there can be n number of stratas. In fact, you can define stratas based on multiple variables. Say, for example, what I can do is, if I am selecting people, what I can say is I will define strata based on age. So I'll say maybe I'll define anything less than 25 as young, greater than 25 as old. Now this becomes 2 stratas. Now within each strata, I will divide them by gender. So now how number of stratas become 4. So stratas can be any n number of types, and it can be based on 1 or more variables, right? Basically, you are defining groups. Now you can define groups in any number of ways, right? So that's your strata. The third methodology is cluster sampling. Now cluster sampling, the first step is same as strata. So in cluster sampling, what you do is you basically divide your populations into clusters or groups, right? You divide the population into groups, and then what you do is you randomly select one group and still get all your observations from there. Say, for example, let's say I have my population is all of the people living in India, right? So my population is all Indian residents. So this is my population, right? Now I have defined my strata or cluster as young male, young female, old male, old female, right? So these now become my 4 groups or 4 clusters. What I will do is, once I have defined these groups, I'll randomly select 1 or 2 groups. So let's say I randomly select one group, and then all my samples will be on from this group. Right? So the difference between strata and cluster is, in cluster, all of your samples are coming from one group. In strata, all of your samples are coming from all the groups. That is the difference.
So if we select one of the cluster, so would that, I mean, that won't
That will
effectively represent the whole population, right?
that will introduce some bias in there, but this is required in some cases.
Okay.
Yeah.
Cluster is not clear.
So the first step is same for both strata and cluster. The first step is you define groups, right? So let's say I have, my population is all Indian residents. I have defined groups as young male, young female, old male, old female. Now, the first step is clear, right? In the second step, if we are doing a stratified sampling, we will go into each and every group and get observations from each and every group. Basis some proportion, right? But if you are doing cluster, we will not go to every group, but rather we will choose one or two groups and get all my observations from only those. So in case of a cluster sampling, my observations come from a specific cluster or portion of the population. Whereas in stratified sampling, it is coming from all stratas of the population. Yes, the advantage is, let's say you have come up with a drug, right? And that drug does not work on northeastern males, right? Male who live in Northeast India, that drug will not work. So when you are testing the efficacy of this drug, you would want to exclude those people from your population, right? Or for example, let's look at the other way around. Let's say you have come up with a drug which is a cure of malaria only for people living in Asia. So when you test that drug, you would select people who are living in Asia, right? You will not select the whole world population. So when you're launching a drug, right? The ideal population is all over, people all over the world, right? But your drug only works for people living in Asia. So what you will do is you will create clusters based on probably say continents, right? And then select the Asian continent and then select all your samples from within it.
So, sir, what kind of sampling we have done? Will it?
I'll come to that. Sorry, what was your question?
I'm saying what kind of sampling we have done. Will it make a difference in what kind of distribution we get as well?
Yeah. So what kind of sampling you do will affect everything that you do.
So normal distribution will be majorly for random variables, the simplified random.
I'll come to that. I'll come to the distribution. Just hold on a second.
Sir, in strata, you talk about ratio. So if we say like
Yes. Huh? Yes. Yes. Sorry. I was talking about proportion, right? So when I say proportion, basically means you will collect data from the sample in the same proportion as they exist in the population. So if
so I have one question.
yes.
So you said like you talk about the ratio in strata. So if we say we have two color balls, black and red, and we can say seven, like
You have
seven
what?
is
You have
there
what?
in
You have
black.
what? Sorry. No. You have what?
So you said about ratio. So
Yeah.
if we have two color balls, black and red, black
Mhm.
they're like seven, and three we are taking in red. So
Mhm.
how many balls we're taking from uh, the variable seven and three? So we take 8 and 2, right? So we are taking ratio now 7 and 3. So how many balls we are going to select?
Calculate what is 70% of 4. 2.8, right?
So how we can select 2.8 balls?
You round off 2.8, na? You round off 2.8 to nearest integer, so
Okay.
it will become 3.
Okay, and 3 and 1 from okay, another one.
Exactly.
Chalega.
Yes.
Fine.
Chalega, chalega. Yes. Yes. Anything else? Okay. Now, having studied all of these mechanisms, the only mechanism, the only sampling mechanism that is used in 99.5% of cases will be simple random sampling. Simple random sampling is used because in most of the cases you will not have the domain knowledge to define the stratas or the clusters, right? You will not have the domain knowledge. So what you can do is you can use simple random sampling and try to get as much data as possible. Okay, that's the only schema that we will be using. Okay. Now, in terms of distribution, irrespective of what sampling you do, eventually everything will follow normal distribution. It's just that if you do different sampling techniques, the mean and the standard deviation will be different, but it will follow normal distribution. Okay. Now, coming to the central limit theorem, which is the next thing. Now, central limit theorem states one simple fact. Central limit theorem states that irrespective of what distribution the population follows, if you collect mean, or if you collect a sample, right, and calculate the mean of that sample will be part of a normal distribution with a mean equal to the population mean and a standard deviation equal to standard error. Okay. Achha. If irrespective of what distribution the population follows, if you collect a sample, suppose I do not know what is the distribution of age in this room, right? But if I collect, say, 3 people here from here and calculate the average of their age, I will know that this age comes from a normal distribution. This average age comes from a normal distribution with a mean equal to the average age of all people in this room and a standard deviation equal to the standard error. Okay, this is central limit theorem. Now, we have applied central limit theorem, or we can apply central limit theorem to get confidence intervals on population mean, right? So, sorry. Yeah. So outliers will always be there, right? Normal distribution also encounters for the fact of outliers, right? So if you look at normal distribution, I told you that normal distribution, the values go from minus infinity to plus infinity, right? So this actually accounts for the outliers, right? These accounts for very large values with very low probability and very small values with very low probability. The normal distribution takes care of the outliers. But what you can ask is, what if I get an outlier in the sample that I've taken? So for example, let's say, let's consider this case of 10 balls, right? Now, let's say I want to know what is the average value that is there in this ball, right? In any ball, what is the average value? So these are numbers, right? What is the average number on top of any ball? I want to understand that, right? The one way to understand that is I take a sample and calculate the sample mean. Remember, Point estimation of population mean is sample mean. Yeah. If I take a sample, let's say the sample that I take turns out to be these two observations, right? Now, if I calculate the average, now the average will be overestimating the population mean, right? What the problem is, if your sample contains an outlier, then you cannot do anything about it because you do not know the population, right? So you will not be able to realize that that is an outlier. Yeah, I mean, so what we do is, you understand the problem. So for example, I do not know what is the distribution of age of Indian male. I do not know, right? Now, if I get 10 random people and note down their age and see 5 of those people have an age above 100 years, somehow I ended up with this sample, right? I will not be able to realize that 100 is actually an outlier because my data says 50% of the people are above 100. Makes sense? So, yeah. How will you make out? You do not know the distribution. You do not know the population. Forget about India. Let's say you go to Antarctica, right? And you tell me the average age of penguins, right? Now, you have got 10 data points, and each of those 10 data points show that, I mean, 50% of the data points have an age of more than 100 years. Now, do you know those 100 years are outliers or not? You have no idea about the average age of, or what is the distribution of age of penguins, right? You do not know, right? So you will not know. To avoid this problem, what we do is we take a large sample. When you take a large sample, by definition, an outlier is an observation which has very low probability to happen. That's the definition, right? If you take a large sample, there is a very low chance that you will get most of the observations which are outliers, right? So you take a large sample. So as a result, what happens is, even if you get an outlier, they will be a minority portion of your sample. Now, once you have outliers as a minority portion of a sample, then we can treat it. Right? Then we can treat it. But if you end up with a sample where the majority of the observations are outliers, then there is no way to treat it. Make sense? Okay. So we'll talk about how you can treat outliers later, but in that context, outliers are defined as very high or very low observations which occur very few times. If outliers occur too many times, then they are no longer outliers. Even in a large sample, right? Say for example, you collect sample, you are trying to measure average income and you collect sample from South Bombay, right? That is the wrong place to collect sample, but somehow you collect it and you will get incomes which are in crores. But that's the data that you have. If 90% of the data is saying that all of the incomes are greater than 1 crore a year, then you cannot do anything about it, right? That is a bias sample. So if you have a bias sample, there is no way to go about it. You will have to live with that sample. But to avoid a bias sample, what we do is we take a large number of observations, so that even if there is a bias, it will get reduced.
So
Okay.
large in the sense more than 50%.
No,
How much
large
you will
means
take?
as large as you can get.
Okay. So like from out of 10, if we are taking 6, we are taking large, right?
Sorry.
From out of 10, we're going to take 6 samples, so we are taking large.
Again, large, there is no definition, right? Large is as large as you can get. If 6 is as the largest sample that you can get, then 6 is the largest.
So how we can decide the outliers are in minor portion?
Sorry?
How we can decide that outliers are in minor portion if we
You
are
can
taking?
hope. You can hope. There is
Okay,
no way to mathematically decide. You can hope that if you take a large sample, you will get out. You will not get most majority options as outliers.
got you.
You can hope. Yeah. Mhm. No, no. Why do you need to know how large? You will take as much data as you can. Mhm. Mhm. Yeah. No, I don't get it. Yeah. I mean, when we did point estimation, I told you, given a data, this is the best estimate that you can get. So that estimate is preconditioned on the data that you already have. It's not the other way around, right? If you have already collected the data, the best guess that you can have basis that data is sample average. Yeah. If you have the domain knowledge, you will probably categorize them as outliers. But if you do not have domain knowledge, that's what I'm saying. Most of the cases, you will not have domain knowledge. So then what you will do is you will take as much observation as possible. And then just hope that most of them do not come from South Bombay. Okay? Or a place where it is biased. Not really. I mean, you will get a normal distribution even in South Bombay, right? There only that the mean will be in crores, right? It will still be a normal distribution. Okay. Increase the sample size. Yes. Yes, that's the only technique. Now coming to central limit theorem. Is central limit theorem clear? Okay. Now I will not go into the whole derivation that we did to get to the confidence interval, right? All of you have written it down. It is not there in this work, this material, right? You should write it down, go over it, and let me know if you have any question. Then we talked about standard error. Standard error is population standard deviation divided by square root of sample size. Then this is confidence interval. We have already discussed this. Yes. Now, apart from normal distribution, there are few more distributions that we will need to use in hypothesis testing. The only place that you will see these distributions is hypothesis testing, right? And these distributions are derived from normal distribution. Okay, I'll explain how. So apart from normal, the other distributions that you need to know by definition, you do not need to know by heart, just need to know by definition, are chi-square, T, F, right? So three more distributions that you need to know: chi-square, T, and F. Okay. Now let's start with chi-square. Chi-square distribution is produced if, let's say, if you have x1, x2, dot variables that follow standard normal. If you have a number of the variables that follow standard normal, then x1 to the power 2 plus x2 to the power 2 plus dot 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 will follow a chi-square distribution. So basically, chi-square is nothing but square of a normally distributed variable or sum of square of multiple normally distributed variables. So for example, if age is normally distributed, if I calculate some metric which is square of age will follow a normal distribution, sorry, a chi-square distribution. If age is normally distributed, age to the power 2 will follow chi-square distribution. No. Age is normally distributed with certain. Let's say age is standard normal, right? So let's say average age is 0. Then if age is standard normally distributed, then square of age will be chi-square distributed.
What exactly is chi-square distribution?
Square of normal distribution. It is a distribution, right? The way a chi-square distribution looks, I'll take you through the shape. The shape is actually not defined. Now, chi-square distribution has only one parameter. That parameter is known as degrees of freedom. Okay. So if I have one variable x1 which follows standard normal, which is n 0 1, then x1 to the power 2 follows chi-square with degrees of freedom equal to 1. Similarly, if I have x1 which follows standard normal and I have another variable x2 that also follows standard normal, then x1 to the power 2 plus x2 to the power 2 follows chi-square distribution with degrees of freedom equal to 2. So degrees of freedom basically denotes how many normally distributed variables have you squared and added up. Degrees of freedom will be 3. We'll come to that. You will realize why we require. Okay. These are, yes.
So mostly, I think we discussed that 99% of the data available will be following the normal distribution.
Yes.
So what kind of data is there which goes into the chi-square distribution?
We'll come to that. I'm telling you, you will see these distributions being used only in hypothesis testing. So you will come to that, right? For now, understand this distribution, right? Now, if you want to know the shape of the distribution, there is no defined shape for these distributions. Depending upon what is the degree of freedom, these distribution take different shape. So for example, so for example, if degrees of freedom is 1, this distribution looks like this. It's basically exponentially decreasing distribution, right? If degrees of freedom is 2, the distribution is the green line. Degrees of freedom 3 and so on. So as you increase the degree of freedom, the shape changes. There is no fixed shape of a chi-square distribution. No. Frequency is not decreasing. Imagine this as, let's say, age is, there are 10 people, right? And they have 2 variables. We have 2 variables on each of those 10 people, age and height. Assume age and height follow standard normal, right? Then if I calculate a third metric, which is age square plus height square, this third metric will have some distribution, right? That distribution will be this green line, chi-square with 2 degrees of freedom. Now imagine degrees of freedom 1 is very easy to explain. I'll explain how. Degrees of freedom, it is, you have to visualize this, right? How does a normal distribution look like? A standard normal. How does a standard normal look like? Bell
Bell
shape.
curve.
A standard normal looks like a bell-shaped curve with a mean at what point? Mean at 0, right? So mean at 0. So this is 0, right? This is the variable. Now if I square these variables, what happens? Negative values all become positive. So these probabilities are mapped to their positive counterparts. So probability of -1 will be mapped to probability of 1, and the probability will double there, right? So if I square a variable, the curve will look something like this, right? One side of the normal. Makes sense? But height will be double, right? So if you look at degrees of freedom 1, just see, it's half of the normal. Degrees of freedom 1 is very easy to understand. What becomes difficult is to visualize it to higher degrees. When higher degrees you don't know, right? Do you understand? This yellow line looks like half of the normal distribution, but with a greater height. Make sense? Okay. So this is chi-square. Now, all of you understand chi-square, and what do you mean by degrees of freedom? You understand what is meant by degrees of freedom?
Yes.
Could you please repeat degree of freedom?
Number of variables you are squaring, not observations. Observations is rows, variables is columns. Squaring and
Okay.
adding. Degrees of freedom is number of normally distributed variables that have been squared and added to get that chi-square. If you are squaring two normally distributed variables and adding, degrees of freedom is 2.
Okay.
If you square this, not the standard deviation, standard normal. Yes. If you square a single standard normal, you get chi-square with 1 degree of freedom. Yes. If you square two normally distributed variables and add them, you get chi-square of 2 degrees of freedom, and so on.
Sir, is there something if we subtract these two square values?
No, there is nothing for subtraction. I mean, you can think of it, right? How can no, there is nothing for subtraction actually. Yeah, there is nothing for subtraction. If you subtract two normally distributed variables, you will probably get 0. There's something around that. Yeah, I don't know. Okay. So this is chi-square, right? The next distribution that we are going to look at is T-distribution. All of you are clear with chi-square, right? Okay. Now, if you are clear with chi-square, T-distribution is derived from chi-square. Okay. Now, if there is a variable x1 that follows normal 0, 1. What is normal 0, 1? Standard normal. And if there is a variable y that follows chi-square with k degrees of freedom, general chi-square, k degrees of freedom, right? Then x1 divided by square root of y will follow a T distribution with k degrees of freedom. You need to know these definitions because these are asked in the interviews. So you need to somehow remember this. Okay, so chi-square is sum of square of normal. Simple way to remember, sum of square of normal. T distribution is a ratio of a normal and a square root of chi-square. Right? Ratio of a standard normal divided by square root of chi-square. X1 is standard normal. Ratio because I am calculating x1 by square root of y, right? So it becomes a ratio, right? Make sense? K is the degree of freedom of the T distribution. This degree of freedom will be exactly equal to the chi-square, which is used to derive the T distribution. T distribution, yes. Nini, you have read now, we'll come there. Just wait. No. Definition is not something else. Did I talk about variance anywhere? So we'll use that. We'll use that. Now, in T distribution has a shape which is very defined. T distribution looks like a bell which has been pressed down. So basically, it's a normal distribution with thick tails. So what happens if you have a bell and you press it down? The bell spreads, right? So it is a normal distribution with thick tails. So since it has thick tails, what happens? The mode will have less probability. The height has reduced, right? You have pressed it down. So the probabilities get distributed to extreme values, right? Remember, because this property is used in a lot of algorithms. In a T distribution, extreme values have higher probabilities than normal. Remember this. If you press a bell down, what happens? The mode goes down. The volume is somehow it has to be spread, right? The volume goes to extremes. So as a result, T distributions have higher probabilities in the tails. They have thicker tails or heavy tails as compared to a normal distribution. Now, having said that, since it is bell, it is still a bell, right? You have pressed it down, but it's still a bell. It's a flattened bell. Now, since it is a bell, it will be symmetric, right? So T distribution, remember, is symmetric about its mean, which is equal to mode, which is equal to median. It looks just like normal, but pressed down. So if you want to visualize the T distribution, this is how our T distribution looks like. This is how it's just like a normal distribution, but pressed down. Oh, if you compare it with a normal distribution, you will figure out. If you compare it with a normal distribution with the same mean, you will figure out. So instead of T, if I had a standard normal here, the standard normal will probably look something like this. It will have higher volume.
So what is this V with it?
V is the degree of freedom.
Degree of freedom as in K?
Yes, K. What we have written as K, yes. Since it is symmetric, mean will be equal to median will be equal to mode. Yes.
This is interesting actually.
No. Since it is pressed down, the tails will have higher volume or higher probabilities. Higher probabilities means higher observations, right? So there is higher chances of higher values coming in or higher chances of lower values coming in. Because the extremes have now got higher probabilities, right? Previously in a normal distribution, extremes had really low probabilities, which means there is very low probability to get very high and very low value. Make sense? Now I have pressed it. So what happened? They have got higher probabilities. Now the chances of getting extreme values have increased. Right? Okay. Now, the third distribution that we are going to study, T distribution is clear? Okay. The third distribution that we are going to study is known as F distribution.
Can you tell us some practical significance of this chi-square and T distribution curve?
We will, right? So I'm telling you to now understand the distributions. We will use them in hypothesis testing.
Okay.
See, I mean, I will not be able to tell you a naturally occurring variable which follows chi-square distribution. I don't know, right? Similarly, I'll not be able to tell you a naturally occurring variable that follows F distribution. Probably none. These distributions occur under very special scenario. We will look at those scenarios. These are all theoretical distributions, right? They do not, probably they will never occur in practice, right? These theoretical distributions are seen under certain special conditions. We'll look at those conditions, right? There is no practical example for them. These are all theory. Okay. Now, F distribution. You understand chi-square and T? Third is F.
What is this DF? You mentioned the
DF is degrees of freedom.
Oh yeah, okay.
K can take any value between 1 to infinity. If, say, I have a variable x1 that follows chi-square with k degrees of freedom, and I have another variable x2 that also follows chi-square with p degrees of freedom, right? Then x1 by x2 will follow F distribution with 2 degrees of freedom, K1, K and P. Because there are 2 chi-square, right? So there will be 2 degrees of freedom here, right? If x1 follows chi-square with k degrees of freedom, y1 follows, x2 follows chi-square with p degrees of freedom, x1 by x2 will follow F distribution with k comma p degrees of freedom. To interpret it very easily, you can imagine F as ratio of square of 2 normal distributions. What is chi-square? Square of normal distribution. This is ratio of square of 2 normal distributions. Make sense? K comma p degrees of freedom. K is the degrees of freedom of the chi-square in the numerator. P is the degrees of freedom of chi-square in the denominator. So the resultant distribution will have 2 degrees of freedom. K comma p.
What was that statement that you're making with the ratios earlier?
Sorry.
You just made a statement now with the ratio, something with the ratio.
Yeah. So you can imagine F distribution as a ratio of square of normal distribution. What is square of normal distribution? Chi-square. Ratio of 2 chi-square, F.
Okay.
See, what is a parameter? These are known as parameters. What is a parameter? Parameter is a number which characterizes the distribution. Remember, normal distribution had 2 parameters, mean and standard deviation. Now, I'll tell you how parameters are derived for each of these. Now, remember, all of these are derived from standard normal, right? All of underlying distributions are all standard normal. Now, standard normal, there is no parameter for it because it is known, 0 and 1. So there is no user input for it, right? So when you are calculating chi-square, what is the only user input? How many normal distribution you square? That is the only user input. So that becomes my degrees of freedom. Similarly, when you are calculating T, numerator is standard normal. There is no input for it. Denominator is chi-square. There is an input. How many normals you want to square? That becomes your degrees of freedom. Similarly, F is a ratio of 2 chi-square. Now for each of the chi-squares, you have a user input which is their degree of freedom. So when you have a F distribution, it has 2 user inputs. The degrees of freedom of the numerator and the degrees of freedom of the denominator. Okay. Now, F distribution also does not have any fixed shape. If you look at the shape of a F distribution, it changes with the value of the degrees of freedom. So if you look at this, the D1 and D2 are degrees of freedom of the numerator and the denominator, right? So if you say D1 and D2 are both equal to 1, which means that it is ratio of square of 2 normal distributions, isn't it? Then it looks like the red line, the distribution. If you change the degrees of freedom, they take different shapes. right? So this is F distribution. Now, the only thing, now let's come to what you need to remember. What you need to remember out of all of this is what is, or how do we get a T distribution, or how do we get a chi-square distribution? This is the only thing that you need to remember, right? And one thing that you need to remember is T distribution is symmetrical. I'll come to it. So for now, degrees of freedom is number of square normals you are squaring and adding. You understand degrees of freedom in this context? You understand it, no? Number of normal distributions you are squaring and adding. That's it. नहीं ठीक है नहीं. What is your question? Mathematically, you understand. You want to understand what is degrees of freedom. Yeah. Okay, it defines, right? Say for example, let's say I have a variable age, and I have a variable height, I have a variable weight, right? All of them, let's assume all of them follow N01. All of them follow, right? Let's assume that. If they do not follow, you know how to make them follow, right? Let's assume that. Yeah. Okay. If now these you understand, right? All of them follow N01. Now, if I calculate a new variable, which is say age to the power 2, this is a new variable I calculated. This variable follows a chi-square, right? Similarly, if I calculate age to the power 2 plus height to the power 2, this follows chi-square with 2 degrees of freedom, right? Curve is 1, right? For this, you get one curve only. This is a one variable, right? So you have one curve for it. 2 degrees of freedom means you are squaring and adding 2 variables. That's it. Yeah. I'm coming to it. So you understand chi-square here, right? Now, if I now say calculate a third variable, which is say age divided by square root of height to the power 2 plus weight to the power 2. Yeah, this variable follows a T distribution. Here there is degrees of freedom, but the generated variable is 1, so there will be one curve, right? Now, let's say I create another variable which is age to the power 2 divided by height to the power 2 plus weight to the power 2. This will follow a F distribution with degrees of freedom 1, 2. Why? Because in the top, I have one single standard normal which has been squared. In the denominator, I have 2 standard normals which have been squared. The curve will be 1, right? The variable is 1. But the shape will be like a degree of distribution of F.
So query, in T distribution, the denominator is a square root, or is it's just a chi distribution?
No, square root of chi. Did I say just chi? Then I made a mistake. I said
square root of chi.
Right? Sorry. In the J column. Not for the age. For the numerator of this ratio, the degrees of freedom is 1. For the denominator, it is 2. Yes. 1, 2. It's a pair of numbers. This is a T distribution with the degrees of freedom 1. Sorry, degrees of freedom 2. इन टी डिस्ट्रीब्यूशन टी में क्या आई स्क्वायर कितने हैं? एक ही है ना, नीचे ही आता है वो, तो एक ही डिग्रीज ऑफ फ्रीडम है। एफ में 2 का स्क्वायर आते हैं ना, तो 2 डिग्रीज ऑफ फ्रीडम है। Okay, now degrees of freedom, here we understand it as number of normals that we square and add. That is a thumb rule definition of degrees of freedom that you have understood from here. But in mathematics, degrees of freedom has a different connotation, right? I'll explain degrees of freedom I'll try to explain it at least in a very simple way. So a degrees of freedom in mathematics is defined as following. If I have an expression which looks like this, x1 plus x2 plus x3 is equal to 4. If I have this expression, this is an expression. Yeah. What is the degree of freedom of this expression? Any idea?
3.
Degree of freedom of this expression is 2. The reason being, out of these 3 variables, 2 can take any random value. Now, once those 2 take a random value, the third is fixed. Right? This is the degree, this is the concept of degree of freedom of the expression. So if you see, if I change since I've fixed their total, right? So 2 can take random values. X1 can take any random value. X2 can take any random value. Now, once X1 and X2 take those random values, X3 becomes fixed. Because the summation has to be 4. Exactly. So degree of freedom is 2. Similarly, if I write x1 plus x2, that's it. What is the degree of freedom of this? 2. Because both can vary. Both can vary. I have not limited it, right? Yeah. Now apply this concept to chi-square. What is chi-square? Sum of square of normal. What will be degree of freedom? Depends on how many normals you are squaring and adding, right? Adds up, right? That's how the degrees of freedom are defined. Make sense? Okay. Okay, so this is T, F and chi-square distributions, and we will see where you can use these distributions. Okay, cool. Any questions? Any question? Okay, now, yesterday we had talked about hypothesis. Sorry, last week we had talked about hypothesis testing, right? Now we talked about hypothesis testing has a few parts to it, right? Now when I say parts, it does not mean that they will come in a particular order. It's just that to build a hypothesis testing, you need those things to be present, right? What are those things? Null hypothesis, alternate hypothesis, you need a test statistic, you have a distributional assumption, and then you have a significance, and you have a p-value, right? Those are the parts of any hypothesis testing. Now, we looked at one hypothesis test in detail, right? And we understood how the hypothesis testing mechanism works. Make sense? We understood how it works, right? Now, having said that, this is the simplest case of a hypothesis testing, because here you see, you knew the population standard deviation, right? And you had a large number of observations as sample, right? In most of the cases, however, you will not be able to apply this scenario, but the concept remains same. It's just that the distribution will change. Here, what was the underlying distribution? In this case, what was the distribution? Normal, right? In the other hypothesis testing that we will do, you will see that we will get T distribution, we'll get chi-square distribution, we'll get F distribution. That's why we talked about those distributions. Okay. Any questions on what we had done the last week? So if you have question, that's good. Because if you do not have question, I'll move on to the next test. No questions, right? Okay. Now, before we move on to the next concept, there is one more thing that I wanted to discuss, which is known as types of error. What kind of error can you make when you do hypothesis testing? Now, understand hypothesis testing is very similar to a court case, right? It is very similar to a court case. Now, if you have seen the judgment from any court case, the judgments might not always be very true, right? In movies, you see, people who actually commit crime, they are set free, right? So in those cases, the judgments are not true, right? Okay. So basis that understanding, let's see how many types of scenarios might occur. One scenario is you pronounce a person as guilty and he is indeed guilty. You pronounce a person as guilty and he is innocent. You pronounce a person is innocent and he is guilty. You pronounce a person as innocent and he is innocent. Make sense? Okay. This case and this case are where our hypothesis resulted in actual or the true decision, right? And this case and this case are the errors. Make sense? Okay. Now let's define those errors. If you reject or if you do not reject the alternate when the null is true. If you do not reject the alternate when the null hypothesis is true, it is known as type 1 error. Okay. And if you reject the alternate when the null is actually false, it is known as type 2 error, right? So type 1 is, in a layman language, type 1 is rejecting the null hypothesis when it is true. Type 2 is accepting the null hypothesis when it is false.
So why we will not going to reject if null is true?
Sorry?
So why we do not reject the alternate when null is true? It's by obvious, like
Because we made a mistake, right?
So in two things, how we can do mistake? There are two things: either null is true or alternate is true.
What I'm saying here is, if in actuality the null hypothesis is true, but while testing we say the alternate is true, then it is type 1 error. If in actuality the null is false, but while testing we say the null is true, then it is type 2 error. Right? Say for example, in case of that petrol price, right? We were testing whether the price is greater than 92 or not. Now, our hypothesis testing told us that the price is indeed greater than 92, right? That is what we found from the testing. But in population, it might happen that the average price is actually less than 92. If that is the case, we have made an error. Then it will be either a type 1 error or a type 2 error.
While calculation. Okay.
Make sense?
Right.
Clear?
Yeah.
Okay. Now, type, yes.
Sir, my second question
null is actually true means population में null hypothesis true था, आपको नहीं पता है? हाँ
अच्छा
हाँ, आप बात नहीं समझ रहे हो. When you do hypothesis testing, you test based on the sample. Yeah. Now the decision that you take on that sample might or might not be true in the population. You understand, right? My point is that I'm saying when you take a decision based on your sample and you reject the null, but in actuality the null was true, then you are making a type 1 error. ये error की बात कर रहे हैं ना? All of you understand this, right? Two kinds of error. So these are types of error. Type 1 and type 2. Type 1 error is what you already know. What is type 1 error? Type 1 error is very easy to interpret. Now help me or remind me what is p-value in a right tail test? What is p-value in a right tail test?
0.05.
P-value is not 0.01, 0.05 is alpha. What is p-value?
0.025.
What is p-value?
p-value is
In this graph,
right
if
2.5.
this is the test statistic value, what is p-value? Area to the right. So p-value is, in a right-tailed case, p-value is area to the right of the test statistic. Yes or no? Okay.
Yeah.
Yes.
Okay. Now, if p-value is area to the right, okay. Now understand what is this area. This distribution, understand this carefully. This distribution that we use in hypothesis testing, this distribution is constructed assuming that the null hypothesis is true. Yes or no?
Okay.
What do we assume in the hypothesis testing? In the first step, we assume that the null is true. Similar to a court case, you assume a person is innocent. Yes? Okay. So this distribution is constructed assuming that the null hypothesis is true. And then what we say is, then if this probability is very low, we say that then our assumption is not correct. Yes or no? Yes, right? Now, what does this probability signify? This probability signifies your margin of error. Because although this probability is really small, but there is still some probability, right? So for example, in the case of oil prices, right? We had constructed this distribution assuming a mean of 92, right? We got a test statistic which is probably, which is, if I remember, 93 point something, right? And since area 93 to the right of 93.6 is very low, we say that the mean is probably not 92 with 5% significance, right? But that does not mean that you are telling it with a certainty, because there is still a possibility that you can get a 93.6 value as sample with a 92 mean. Because there is still that right side is that probability, that evidence, right? Do you understand? What is the right hand side area? Right hand side area is the probability that the null hypothesis is true, isn't it? Understand this. This distribution is under null hypothesis. So area to the right is what? Probability that you have got the sample and the null hypothesis is true. If that probability is very low, we say our assumption is false, right? This p-value is nothing but type 1 error. So p-value that you calculate is actually a measure of type 1 error. If the type 1 error is really low, you will say I reject my null or I do not reject my alternate. Think about this, right? So what is this right side area? I mean, again, take a very intuitive example. Let's say a test statistic is nothing but a evidence, right? Let's say that you have got a evidence that the accused person's fingerprint is on the knife and somebody has actually seen him stabbing that person, right? But still there is a probability that he is innocent, however small, right? There's still that probability. Yeah, that is your type 1 error, right? So the area to the right, or basically the p-value that you calculate, is a measure of type 1 error. If the type 1 error is less than a certain value, we say that we will reject the null. Yes, so what is type 1 error? Type 1 error is you reject the null, but actually it is true, right? So before rejecting the null, you need to make sure that your probability for making a mistake is really low. That's why we look at a very small value of p before rejecting null. So before pronouncing somebody as guilty, you need to be sure that his probability to be innocent is really low. P value is that probability to be innocent. If that is really low, you reject the null. Make sense? Okay. Now, what we'll do is we'll take a break here and we will continue from here after 10 minutes.
So one question is here.
Why not decrease the significance level? To what extent? It will never be zero, right? You cannot have a zero significance. 5% is a universal, you can say, thumb rule, right? People say that if you are 95% sure, this is sure enough for me, right? So that's why the 5% comes.
So one question is here.
No, you assume the distribution, right? Now, after you assume the distribution, you say, if my probability to be wrong is less than 5%, I am happy to live with that uncertainty. There comes the 5% significance, right? Now, what is your question?
So p value is the probability value what
type
we
1
are
error,
going to prove. Yes, one.
No, you calculate that. You calculate that basis the null assumption. You do not know. You do not know.
You're calculating. Okay.
No. What I'm saying is, you do not need to have a conceived knowledge of type 1 error, right? What I'm saying is type 1 error is something which comes out as a byproduct of hypothesis testing. So in hypothesis testing, you assume a certain distribution basis a certain theory. That theory is true. Everybody knows that, right? Now, if that theory is true, then the null distribution is also true. Now, if the null distribution is true, then the probability of the mistake is also accurately calculated, right? So that is the type 1 error. You calculate the type 1 error. You do not need to know it from before. P value is nothing but type 1 error. Okay, yes. What was the question from online? There was a question from online, right?
Sir, for type
That is
2
clear.
error.
For type 2 error, yes.
Yeah, for type 2, this 92 was false, right? And we accepted, if we rejected 93.6 and we accepted 92, right? So, so anything towards the right side of 92 is type 2 error.
No, type 2 you cannot calculate in this way.
Oh,
Type 1 is easy to understand. Type 2 is not that easy to understand using this distribution. Type 1 is easy to understand. Yes, anything else?
So can we do a practical question in calculation of type 1 error?
You did. In last week, you actually calculated the p-value, right?
That is right.
That is the type 1 error.
The p-value is the type 1 error, is what you said.
Exactly.
Okay.
P-value is that type 1 error. If the type 1 error is very low, probability of type 1 error is really low, then you are confident with your decision. Right?
Okay.
Type
So
2 error
that's,
cannot be measured directly. Yes.
in other words, the nomenclature of p-value is actually type 1 error.
Exactly. You did not take. P-value was calculated not as 0, but a very small quantity. It is never 0. So it means that your probability to make a mistake is really small. It will never be 0. 0 will come if your test statistic is infinity. That will never happen. No? Thank you. So we will take a break now. Okay, now let's get started. Yeah. Now, the next thing that we are going to do now is look at all scenarios where we would typically do a hypothesis testing. Okay, so 1, 2, 3, 4, 6. These are 6 scenarios of different hypothesis testing. There are different tests that are there to tackle each of these scenarios. Please share best book name. There is no best book. Again, there is a book called Machine Learning Using Python. But if you are not from a stats background or have never done machine learning before, do not read it. You will not understand. Okay, now coming back to this description or this case study, right? Now, what I would tell you is take 30 seconds to read through these lines, the first 4 lines. Done? Okay. Now, so let's now look at the data that we have. Okay, so this is the data that we have. The data is from a credit card campaign which was done by a particular bank, right? Now, all of you understand what do I mean by a campaign? Campaign means they'll call you or they'll do some ad campaign or whatever, right? Now, why do banks do campaigns? Why do banks do marketing activity?
To promote their insurance.
Why do they promote their product? To gain money, right?
To get benefit.
Right. So basically, when banks do any marketing, they are trying to increase only one thing, specifically in credit card usage. They want you to use the card more, right? Okay. Now, having said that, let's look at the data. The first column is customer ID. This is a unique ID of a bank, right? Then you have gender. Then you have acquisition channel. Acquisition channel means whether you have been acquired through internet or you have directly called in or you walked into a bank. What was the channel through which you got that credit card, right? Yes. Something, right? 4 might be you walking in. Yeah. Then you have region. Banks usually demarcate regions, right? They might have north, south, east, west. This basically tells you which region you belong. Makes sense? Then you have marital status. All of you understand what this is. Then you have segment. Segment basically means what is that plastic that you hold. Plastic means in a card, you might have a diamond, you might have a platinum, might have whatever, gold, whatever, right? So you understand there are types of cards, right? So segment basically means the type of the card. All of them are credit card, but there are types. Pre-usage. Pre-usage basically means the usage pre-campaign, right? Post-usage 1 month means usage 1 month after the campaign. Something, sir. 57 might be 57%. We don't care. The only thing that you need to know is higher this amount, more is the usage. That is the only thing, right? Latest month usage. Latest month usage is usage as of last month. Remember, this campaign was conducted 1 year before. So this is usage as of last month. Post usage second month means usage 2 months after the campaign. Make sense?
What this channel you said?
Yes, sorry.
Channel.
Channel means what was the channel through which you were acquired, whether you walked in, you applied for the card over the internet, whether you called in to apply. So these are the channels.
So what this 4 denotes?
4 denotes one. So it's a categorical variable, right? So it basically denotes one type of channel.
Okay.
I do not know which channel. But it denotes one type of channel.
We assign 4 to a particular channel.
Yeah, 4 is one type of channel. Yes.
Okay.
Okay. Now I see. I understand that all of you need to know the data, but for this particular case studies that we are going to solve here, you do not need to know what each number means, right? So you just need to know broadly what the variable indicates, right? Okay. Now, but when you are working on the business, then you need to know what those numbers mean. Here, not required. Okay. Card. Let's read the first statement. What is the first statement? Correct. So card usage has been improved significantly from the last usage or last year usage, which is 50, right? So what is my null hypothesis here? No, null hypothesis is current card usage is 50. What is the alternate? Card usage greater than 50. It has increased, right? They want to test whether it has increased. So alternate is greater than 50. I told you business input will always be alternate. So what does the business want to test? Whether it is greater than. So we'll do a right tail test. Make sense? Okay. Now, in this case, can we use the same technique that we did last time? Yes, we do not know the standard deviation. Because in the last case, we knew the standard deviation, right? If you do not know the standard deviation, then the test that you will do is one sample t-test. What is one sample t-test? One sample t-test is a hypothesis testing which is done to see whether the population mean is equal to a certain value. Here, we want to test that, right? Whether the population mean is equal to 50 or not. 50 or greater than 50, right? So we will use one sample t-test. Okay, you just need to remember this. Do not need to know the test statistic. You do not need to know what is going on under the hood. What you just need to know is, given this scenario, you need to use one sample t-test. Make sense? Now, what is the scenario? If I write it down, if you have, so what is the general business scenario? General business scenario is somebody wants to test if the mean of the population is equal to some value. That is the generic scenario, right? Okay, so this is the scenario S. S can be of two types. Either you know the standard deviation, no means K, or you do not know the standard deviation, do not means D, right? If you know the standard deviation, then the test that you are going to do is what test?
Z-test.
You will do the test that we had done yesterday, which is known as Z-test. The test that we had done last week is Z-test. Okay. If you do not know the standard deviation, the test that you are going to always do is T-test. Right? Simple. Know the standard deviation, Z-test. Do not know the standard deviation, T-test.
But sir, for T-test, sample size should be less than 30, right?
Not necessarily. You can do it even for sample size greater than 30.
Okay, but in books it is written less than 30. So we can.
Yeah, but you can also do the T-test for greater than 30.
Okay, thank you.
Okay, so I am simplifying this. Right? Some statisticians say that if the sample size is greater than 30, you can still do Z. But to simplify this, always remember one thing: standard deviation given, Z-test; standard deviation not given, T-test. Simple. You do not need to bifurcate this scenario again. No, that has nothing to do with this. We'll come to that. That property has other applications. We'll do T-test because if the standard deviation is not known, the test statistic that we will use follows a T-distribution, right? What is that test statistic? The test statistic will be sample mean minus the null value of the population mean divided by sample standard deviation. Remember sample standard deviation, not the normal standard deviation, n-1 wala, divided by square root of sample size. This metric that you see follows a T distribution. Why does it follow a T distribution? The reason it follows a T distribution is X follows normal in most of the cases. I mean, this is how I remember it. X follows normal, right? Okay. Now, what is standard deviation? Standard deviation is square root of sum of square of certain things, right? Remember standard deviation, square root of X minus X bar square. So when you square a normal distribution, what happens? Chi-square, right? And you take a square root of that, and in the numerator you have normal. So normal by square root of chi-square, you get a T distribution. Make sense? Numerator is normal, denominator is square root of square of normal. Make sense? So this becomes a T distribution. So that's, again, you do not need to know this, right? What you just need to remember is if you want to test for mean and you do not know the standard deviation, use one sample T-test. Make sense?
I forgot. What is mu?
Mu is mean.
X bar is also mean.
X bar is sample mean, mu is population mean.
Sir, what is the difference between sample mean and the normal mean?
What is the difference between?
Sample mean and only mean, sir.
Sample mean is mean calculated on sample, and I don't know what is only mean. Only mean is only mean. I don't know. Mean is a measure, right? If you calculate on a sample, you get sample mean.
Okay.
And if if you calculate the mean on the population, you get the population mean. Do you understand? Okay. Okay. So this first one is one sample T-test, right? So the generic statement that you should remember is one sample T-test. If in a one sample T-test scenario, the null hypothesis will look something like this. H0 will always say mean is equal to a value. This will be what a H0. This is what a H0 will look like, right? And H1 can be three things: mean, mean greater than that value, or mean less than that value, or mean not equal to that value. It can be three things. But the way you identify the null hypothesis, this one sample t-test is, it will look something like this. And SD is not known. In 90% of the cases, you will encounter a case where standard deviation is not known. Right? So in most of the cases, you will actually do a t-test. Make
Sir, one
sense?
question is there.
Yes.
So I'm understanding like one sample t-test is done when we do not know standard deviation. So
Yes.
how we come to know the values from this first uh, sentence? Could you please again
Which
tell
first sentence?
with sir? Could you please open that page? The another one.
This
Yeah.
one?
So yeah, reading this, what we have come to know.
Yeah. So, I mean, you reading this page, what is the null hypothesis? What is the null hypothesis? Null hypothesis is mean is equal to 50, right?
Yeah.
Next question is, do I know the standard deviation? No. So I have to do one sample t-test. Right? Two things. One, am I testing for mean? Yes. Do I know standard deviation? No. So t-test.
No. Okay.
We will understand.
Okay.
The next question will clarify that. Okay. Now, the next one. Read the next one. Yes. So last campaign was successful in terms of usage of credit card. What is the null hypothesis here? Why did banks do campaigns?
To get benefit.
That is the criteria. Okay. So the criteria is usage has increased, right? So what will be the null hypothesis? Null hypothesis is pre-usage is equal to post-usage. Alternate is pre-usage less than post-usage, right? In this case, we will do a paired sample t-test. Why paired? Because there is a before after scenario. For each observation, you have a before value and a after value. Because therefore, each observation gives you pairs of values. So we use a paired sample t-test. That's why previous one was called one sample. Because we were talking about only one sample. Here, we have two samples coming from the same observation, right? Each customer will have a before value and after value. So each customer gives you a pair of value. So we use paired sample t-test. T-test, paired sample t-test. Okay. So how do you identify a paired sample t-test? Paired sample t-test, the null hypothesis will look something like this. Mean of sample 1 is equal to mean of sample 2. This is how the null hypothesis will look like. Alternate can be again of three types, right? Alternate can be mean of sample 1 greater than mean of sample 2.
Yeah, right. Or
It can be
less than.
mean of sample 1 less than mean of sample 2. It can also be mean of sample 1 not equal to mean of sample 2. Right? This is known as paired sample t-test. Why is it called paired? You have to look at the data. I mean, the easier way is to look at the data and then understand. paired basically means, so you understand there are two samples here. One is the before sample, another is the after sample. There are two columns here. Now, when I am testing, from each line, you are actually getting two values, before value, after value. So for one customer is giving you a pair of values. That's why it is called a paired sample t-test. Because values come in pairs. Yes. Second point, what are we trying to test here? We were trying to test whether the campaign was successful. Successful means what? Usage has increased. So what is after the campaign? So what are we going to test? We are going to test whether the average or the mean of pre-usage is actually less than mean of this, right? So the null hypothesis is their means are equal. Alternatives is pre-usage less than post-usage. So this becomes a paired sample t-test. Make sense? Okay. Now, let's look at the third question.
Sir, paired sample t-test is case of like it is like a pre and post kind of thing, right?
It is usually a pre and post.
Means same data before certain scenario and after certain time. Right?
Correct.
Thank you.
Now, third. What is the third one? Third one is talking about, is there a difference between male and female in terms of their credit card usage? Now, here, can we do a paired sample? Here you understand there are two samples, right? Male and female, two sample. Can we do a paired sample? No, because it cannot happen that a person is both male and female. Cannot happen, right? So male sample is totally different from the female sample. You get only one value per row. Previously, we were getting two values per row, right? Here, if you look at the data structure, a person can only be male or female. So I am getting only one value from that row, right? If it is male, it belongs to the male population. If it is female, it belongs to the female population. I do not get multiple values from the same person. Or can I? I can't, right? What I am going to test here is whether the latest month usage is same for male and female or not. My null hypothesis is latest month usage of female is equal to latest month usage of male. Alternate is latest month usage of female not equal to latest month usage of male. Make sense? Do you understand? Okay, now, so the generic, if I talk about the generic format of two sample t-test, then hypothesis will look very similar to a paired sample t-test, right? The hypothesis will look very similar, but the difference is samples are independent of one another, right? There are two different samples here. Previously, we were talking about before and after usage of the same person. But now we are comparing two different samples because it's gender. Sorry, mean of? No, parameter is different, right? Parameter, mean is the parameter. Mean of sample one with one population. You understand what I'm trying to say? I'm really bad in writing. Write it in the way that you understand. Right? You do not need to write this exact thing. Right? You understand what I'm trying to say, right? Write it in a way that you will understand.
Sir, there is one request. If you can save this notepad and send it in the mm, documents when they will be loaded.
Okay.
Sure.
Okay, so this is 2 sample t-test, right? So far we have done 3 tests here. 1 sample t-test, paired sample t-test, and 2 sample t-test. Okay. Yeah. Exactly. So we are basically testing the same thing. It's just that here the samples are related to one another. Here they are not related. Right? Testing the same thing. That's the only difference. That's why they are called paired sample and 2 sample. Related. Yeah. Related. Related means you get values, 2 values from the same person. One value, one person. Because here a person cannot be both male and female. Na? They'll only belong to one class. Okay, now what we are going to do now is basically use them in Python and see what we get.
So, like in this case, we use 2 samples t-test. Can we have n sample t-test as well?
Can we have?
Because here we have classified the columns as male and female.
Uh-huh.
Any case, if we have more classifications,
Yeah,
like
we will do it. We'll do. Yeah. What type? What like this means? The credit card usage. So what is the business statement? What is the business statement? Business आपको ये नहीं बोलेगा ना credit card sample, credit card usage by mail pre-campaign and post-campaign. This is not a business scenario. आप टेस्ट क्या करना चाहते हो? यानी क्लब तो कर रहे थे वो, मतलब उसको क्यों करना चाहते हो? आपको क्या मिलेगा उसमें से? यानी I understand you have a right point, but उसको क्लब करो, फिर मैं उसको ब्रेक करता हूँ. आप क्लब करो. आप देखना क्या चाहते हो? आप देखना ये चाहते हो कि मेल एंड फीमेल प्री एंड पोस्ट कैंपेन दोनों में डिफरेंस है कि नहीं, है ना? तो आप इसको क्या करोगे? इसको दोनों पार्ट में तोड़ोगे. पहले आप डेटा को मेल फीमेल प्री पोस्ट 4 पार्ट में तोड़ दिए, फिर आप देखो मेल प्री मेल पोस्ट, ये पेयर्ड सैंपल हो गया. फीमेल प्री फीमेल पोस्ट, ये पेयर्ड सैंपल हो गया. दोनों में से आपको कंक्लूजन मिल जाएगा, पर एक ही बारी में नहीं करता, तो अलग अलग हो. Just I will find this. Wait, you understand the scenarios, right? You just need to understand the scenario. Doing it in Python is really easy. Okay. Apart from NumPy and Pandas, the only module that we will require here is scipy.stats. From scipy.stats, we will require functions which do this hypothesis testing. Right? So remember the name of the module, scipy.stats. Now, the first thing that we do is we load the data. All of you understand how loading happens, right? We've gone through this. Okay. The data looks like this. We have already looked at the data. Okay. Now, if you want to know the column names, you write data frame dot column names.
So can
No.
you please show the package name?
SciPy.stats. No, stats is a submodule within SciPy. Now let's look at what was the hypothesis. हाँ. डॉट का भी कर सकते हो. Okay. The first hypothesis that we had was credit card usage has improved significantly from last year, which was 50. So my null hypothesis was mean credit card usage currently is 50. Alternate is it is greater than 50. Okay. Now, how do I do it in Python? So what I do is I use scipy.stats, which I have named as stats. And within that, I use T-Test one sample. Right? We're doing one sample T-Test. So T-Test underscore one sample. Within that, I pass on the column with the latest month usage. This is my sample. I pass on the sample and then I pass on what is my null hypothesis. Right? Two things, sample and null hypothesis. That's it. If you run this, you get two things as output. The first thing is known as the value of the test statistic. The second thing is p-value. First one is test statistic, second one is p-value. Okay, now how do I interpret these, right? The way this is interpreted is you have to understand Python can only do a two-tailed test. Python cannot do a one-tailed test. Be it right, be it left, it cannot do anything. It can only do a two-tailed test. Now, how do I, but in our case, we want to do a one-tailed test, right? We want to do a right-tailed test. How do we go from a two-tailed output to a one-tailed output, right? So if you remember how we did two-tailed test, in a two-tailed test, T distribution looks exactly like a normal distribution, flattened, right? Let's say this is T, right? A two-tailed test here is done in such a way that if this is the value of the test statistic, what you do is calculate area to the right, get minus of that value, calculate area to the left of that, right? So if this is T, T means the test statistic, this is minus T. Calculate area to the right of T, calculate area to the left of minus T, right? This is your p-value. But in our case, I only need area to the right. So how do I get area to the right? Divide by 2, exactly. So if you want to convert a two-tailed test p-value to a one-tailed test p-value, you simply divide it by 2, right? So this p-value, is it greater than 5% or less than 5%? Less than 5%. If I divide it by 2, it will still be less than 5%. Okay, so I know my null hypothesis is not true. Makes sense? Okay, now Python does two-tailed tests, right? So not true might mean greater than, might mean less than, right? How do you identify the direction? Direction is given by the sign of the test statistic. If the test statistic is positive, it means that it has done right tail test. If the test statistic is negative, it means the left tail test is true. Make sense? Not equal to might be two things, right? Not equal to might be greater than, not equal to might be less than also. If the test statistic has a positive sign, it means sample mean as indicated, actual mean is greater than the null value. If it is negative, it will mean actual mean is less than the null value. Positive means actual greater than null. Negative means actual less than null. In our case, what is the business conclusion? Has the usage increased or decreased? Increased, right? Because it is showing a positive sign, which means actual mean is greater than null. What was our null? 50. So the actual usage or the actual average usage has increased from 50. Make sense?
Sir, it is using alternate testing now.
The value will be different. You only need to consider the sign. If the sign is positive, it means an actual mean is greater than null. If the value is negative, actual mean is less than null. Sorry. Null hypothesis में जो value आपने लिया था?
Sir, my internet
1.4
got
कहाँ से मिला?
disconnected.
P value has nothing to do with the quantity of increase, right? P value only tells you what is your type on error. And this is not 1.4. This is 1.4 into e to the power minus 39. It's a very
Sir,
small.
when the static is positive, what it mean?
Statistic positive means the null, the actual mean is greater than the null hypothesis mean. Negative means actual mean less than null hypothesis mean. No. Hypothesis
Sir,
testing is not about that, right? Hypothesis testing will only tell you whether your hypothesis is true or false.
Sir, one question here. How did you
It only
import
means that
this
your
library?
decision to say that the actual mean is greater than null mean can be false with a probability of this. Yeah. Or in the other words, your decision to say that the actual mean is greater than the null mean is true with a probability of 1 minus p value by 2. We are rejecting the null.
Sir,
And we are
please
using
repeat the last line.
Sorry?
Please repeat the last line, sir.
No,
1
you don't
minus.
last time. I was answering a question.
Okay.
That's fine. Yes. हाँ, Poppin is a Q. Poppins means population mean. आपका null hypothesis में population mean क्या है? ये keyword है. ये keyword है. Okay. Do you understand the output now? Okay. Now, the next output you need to interpret on your own. Okay. Now, what was the next hypothesis? The next hypothesis, the null hypothesis was pre-usage equal to post-usage. And alternate was pre-usage less than post-usage. Okay. Now,
Sir, we can take any alternate. Now we can also consider pre-usage greater than post-usage. Can we also do that?
sir, look at the problem statement. Na? Problem statement mein what is it saying?
Last campaign was successful in terms
So
of.
it means that they want to test that pre-usage is less than post-usage. Then
Okay.
only will say this campaign was successful. If they want to test whether the campaign was unsuccessful, then we would have used the reverse. But they will never test that, right? Okay.
Sir, one question here. What library we are using to use this pre-usage and post-usage sort means, because my internet got disconnected for a minute. Above. Okay.
Pre-usage, post-usage is coming from the data. To do the
Yeah.
hypothesis testing, we are using scipy.stats.
Okay. Okay.
Now, the next hypothesis will be a paired sample t-test, right? In a paired sample t-test, we use scipy.stats. From that, we use t-test underscore rel. Rel means relative sampling, right? T-test underscore rel. Here, what you do is you input the post usage and you input the pre-usage, right? Because there is no null value. The null is both are equal. There is no value, right? So as soon as you run this, you get two things as output. The first one is statistic. Second one is p-value, right? Now in this case, are we doing a two-tail test or a one-tail test? One-tail test. Pre-usage is, in the business case, are we doing a two-tail test or a one-tail test? One-tail, because we need to test pre-usage is less than post-usage. Okay. So the p-value, is it less than 5%? This p-value, so divided by 2 will still be less than 5%. Make sense? Okay. So we know that the null hypothesis has been rejected. Now we need to know in which direction, right? A positive sign here indicates whatever you have entered as A is more than whatever you have entered as B. A positive sign indicates A is greater than B. So if I reverse this, right? If I put this as A and put this as B, you will see that you will get the exact value, but the sign will flip. If you run this, sorry, sorry. See the this sign just flipped. Everything else remains same. What does this negative mean? Negative means A is less than B.
Less than B.
Make sense? Now, what will be the answer to this question?
That last campaign was successful. I mean, we can accept the alternate here.
Sorry? No.
We can accept
the business will not understand what is alternate. Now, what is the answer to this question?
That the last campaign was successful.
So last campaign was successful. I have taken post usage after 2 months. You can take after 1 month. Your choice. तभी तो successful बोल रहे हैं.
Sir, when the static is negative, means A is less than B.
Yes, A is less than B. Okay, third test. Third test, what are we trying to see? We are trying to see whether usage of male and female are equal. Here, are we doing a one-tailed or a two-tailed test? Two-tailed. We just need to know whether they are equal or not equal, right? Now, in this particular case, the function that we will be using is, yeah, so we will be using stats.t-test underscore independent, right? Because it is independent sampling. Previous was related. This is independent. Now here also you need to give two things, A and B, right? And there is an option called equal variance. Always keep it as false. I'll tell you what this means, right? Always keep it as false. Now, if you run this, you get two things as output. Okay, so before running this, what we need to do is separate out the male and female, right? Because they are in the same data frame, right? So here what I do is I separate out the male and female based on gender, right? Then what I do is then I have male spend here, female spend here. Okay. Actually, these between these codes, I had done it for something else. Remove this. So you have male spend here, female spend here. Make sense? Okay. Now, if I run this, I will get two things as output: test statistic and p-value. Okay. Now Python by default will do a two-tail test, right? So we are also trying to do a two-tail test. So basis this, we reject the null hypothesis, yes, because this is less than 5%, right? Now, if we had to do a one-tail test, right? If we had to do a one-tail test, tell me what does this sign imply?
Is male
A
expand
is less than B, right? Which basically means male spend is actually lesser than the female spend.
Female spend.
Clear? This is how you interpret the hypothesis testing. So bottom line, what you just need to remember is function name and two things. Test statistic value, what does it mean? Oh, sorry, test statistic sign, what does it mean? And p-value. That's it. Clear?
Sir, I'm not able to understand how we are saying that we are doing one-tail test and two-tail test here.
Okay, so look at this statement. What does this statement say? Statement says, is there any difference between male and female usage? Right? If you look at this statement, what they just want to understand is whether male and female usage are equal or not equal.
Okay.
So this becomes a two-tail test, right?
Okay.
In the previous case, it was one tail because they wanted to understand whether the usage has increased.
Okay, got it, got it.
Yeah.
Got it.
So
Yeah.
it depends
Like
on
why-
the business question. Yeah.
Means if we are comparing, then two-tail test.
Sorry?
Like if we are comparing, then it is two-tail test.
If if the alternate is not equal to, then it is a two-tail test. Yes. No, they are not interested. P-value is given as a caveat in those small alphabets. Nobody can see. You will just give it, right? This was the p-value because you just want to save your back. Yeah. So you want to save your back, right? Today, if you said male spend is greater than female spend, and later they found out that it was not, then you can always fall back and say, I told you that this with this much probability, right? So that's why. But you will answer them as yes or no. Okay. Yes. बिजनेस वन टेल, बिजनेस को वन टेल चाहिए तो आपको तो वन टेल में ही आंसर देना पड़ेगा ना. आप बिजनेस को ये तो नहीं बोल सकते ना पाइथन मुझे टू टेल टेस्ट देता है. हाँ. नहीं, आपका क्वेश्चन क्या है? इसीलिए हम वन टेल में कन्वर्ट कर रहे हैं क्योंकि बिजनेस इज इंटरेस्टेड इन दैट वन टेल्ड आंसर. आप अगर क्वेश्चंस देखोगे ना, दे आर ऑल वन टेल्ड, राइट? That's why. P-value by 2 and looking at the sign of the test statistic. P-value by 2 will just tell you whether you're rejecting or accepting, right? But you need to know on which side. Yeah, two-tailed test, just P-value is sufficient. Okay, so these are the three scenarios. Now let's look at the fourth scenario. Now, what is the fourth scenario? You guys are fine, right? It's not getting too heavy or anything. Okay. If it gets heavy, let me know. We'll stop there. Okay.
Can I ask one question regarding scenario 1?
One second, I'll come to the online question. What were you saying? Yes. The value of the statistics does not signify anything. The sign signifies in which direction was the hypothesis rejected. The value does not mean anything. No, it will not. No. No. We are not. We are just interested in yes, no. How is the? Yeah. I am not saying that it does not mean anything. I am saying that we are not interested in it. It has a meaning. We are not interested in it. No. So basically, I'll explain using one sample t-test, right? One sample t-test, the test statistic we looked at, right? So test statistics is sample mean. Test statistic is sample mean minus null value divided by sample standard deviation by square root of n, right? This value is this, the test statistic value. But we are not interested in this. We just need to know the sign. Yeah, I was coming to that. Sorry, I missed that. Okay. Okay, so there is an option that is there which says equal variance. We will always keep it as false. The reason, if you say this is true, it will mean the variance of male spend is equal to variance of female spend, right? But do you know that they're equal? So always keep it as false. If you do not know, or if you have not been informed that the variances of the two populations are equal, always keep it as false. Okay. If you know that the variances are equal, then keep it as true. Which would what? According to the p-value, tell me what was that rule that you needed to remember? P-value 5%, you accept. Yeah. So is p-value greater than 5%? No, not from the T table. It is that one that I showed you. The calculation that I showed you. It is that calculation. The p-value is coming from the T table. Yeah. You can do it. Okay. Now, is any other question? Yes, sir. Yes. Because it followed what distribution? That's why Z table. This follows T table. Okay. So there is table for every distribution. Abhi to you have Python. Na? In 15 years back, there was no Python. People used to actually go to the table and look at the probability. वो जो table होते हैं ना, the book costs 50-60,000 rupees. It has tables for every distribution, like 100 plus distribution. हाँ. अभी आपको बस काम करने के लिए ये रिमेंबर करना चाहिए फंक्शन क्या है, p वैल्यू क्या है, t वैल्यू का डायरेक्शन क्या है. That's it. Okay. देखते हैं ना. T table, right? So T table. Yeah. So where do you see n-1? कहाँ 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 कौन से फॉर्मूला में बोल रहे हो आप? अच्छा, सैंपल स्टैंडर्ड डिविएशन में n-1 क्यों यूज होता है? अच्छा अच्छा, प्रैक्टिकली मैटर नहीं करता है. से if you have a sample size of 100, 1 by 99 is same as 1 by 100. पर ये होता क्या है कि I'm thinking of easier way to explain. आप लोगों ने कभी कॉन्वर्जेंस टेस्ट किया है किसी भी फंक्शन का? मतलब मतलब इसमें एनालिसिस में होता क्या है? So you take a measure on the sample, right? Let's start with mean, right? So what I'm trying to estimate population mean, right? And I'm trying to find out one measure which gives me best guess of population mean. तो मैं एक तुक्का लगाता हूँ, चलो सैंपल मीन ट्राई करके देखते हैं, ठीक है? तो सैंपल मीन है क्या? सम ऑफ x by n, ये है ना सैंपल मीन. तो फिर हम क्या करते हैं, एक सब्जेक्ट है रियल एनालिसिस बोल के मैथमेटिक्स में, उसमें क्या करते हैं, ये एक्सप्रेशन, राइट? व्हाट विल डू इज विल इंक्रीज द साइज ऑफ n एंड टेक इट टिल इंफिनिटी एंड टेस्ट द कन्वर्जेंस ऑफ दिस फंक्शन. कौन से वैल्यू पे ये कन्वर्ज करता है जब n जाता है इंफिनिटी. तो हम ये देखा गया है, ये वैल्यू कन्वर्ज करेगा पॉपुलेशन मीन पे, ठीक है? सिमिलरली जब स्टैंडर्ड डिविएशन एस्टिमेशन की बात आती है, तो एक तुक्का किसने लगाया था, चलो सैंपल स्टैंडर्ड डिविएशन ट्राई करके देखते हैं. तो सैंपल स्टैंडर्ड डिविएशन जब n टेंड्स टू इंफिनिटी होता है, सैंपल स्टैंडर्ड डिविएशन एग्जैक्टली जाके कन्वर्ज करता है पॉपुलेशन स्टैंडर्ड डिविएशन. अगर इंस्टेड ऑफ 1 by n-1 आप यूज करते हो 1 by n, तो वो कन्वर्ज करता है इस चीज पे. समथिंग लाइक दिस, इस चीज पे कन्वर्ज करता है. तो इसलिए हम n-1 यूज करते हैं ताकि ये वो हो जाए, कैंसिल आउट हो जाए, राइट? बट आई मीन यू डोंट नीड टू नो दैट, राइट? सो फॉरगेट दिस. Okay.
So can we try yesterday's oil example with Python if it is possible to calculate?
Yesterday's oil example. Okay. Sure. I don't have the backend data for it. That's the problem. I don't have the actual Excel data, right? That's why I won't be able to do it. If I had all the Excel data, I would have fed it into the function.
Okay. Right.
Yes. The third point, look at the statement. Is there any difference? So the alternate is not equal to. There is a difference. That's why two-tailed. ग्राफ मतलब नहीं, आपका क्वेश्चन क्या है, ये क्यों टू टेल्ड है? तो उसके लिए कर्व में जाने की जरूरत नहीं है ना. बिजनेस क्वेश्चन क्या है? नॉट इक्वल टू मतलब टू टेल्ड है ना. अगर बिजनेस ने पूछा होता कि मेल ज्यादा स्पेंड करते हैं क्या, तो इट विल बी वन टेल्ड. हियर यू जस्ट नीड टू नो वेदर दे आर इक्वल और नॉट इक्वल. Okay, now one last test before we close for the day. Look at the fourth scenario. ठीक है? Okay, now अभी डेटा पे चलते हैं. Okay, let's look at the data. So how many segments do we have? We have 3 segments. We have 3 segments, right? Okay. Now, what is the null hypothesis? Null hypothesis is H0 is mean of segment 1 is equal to mean of segment 2 is equal to mean of segment 3. This is the null hypothesis. Yeah. Okay. What is the alternate? Alternate is at least one is not equal. Right? At least यहाँ पे 2 equality है, at least एक गलत है. ठीक है? Now, this scenario can be tested in 2 ways. Either you do multiple t-tests. Multiple t-test होगा ना इसमें 3 scenario. तो 3C2 test होगा. 3C2 understand? Combination. 3C2 means how much? 3 into 2 by 2 factorial. 3 tests होगा. 3 tests होंगे ना. So you will test whether segment 1 is equal to segment 2, then segment 1 is equal to segment 3, then segment 2 is equal to segment 3. अगर आप 2 तरीके से कर सकते हो. 3 t test करो, उसमें से एक में भी अगर null hypothesis reject हो गया तो you reject the null. Right? Second way to do it is by using another hypothesis testing known as ANOVA. Right? ANOVA. ANOVA. ANOVA stands for Analysis of Variance. This is known as ANOVA. Now, ANOVA का generic format क्या है? Generic format है mean of sample 1 is greater than is equal to mean of sample 2 is equal to mean of sample 3. मतलब 2 से ज़्यादा अगर sample है तो 2 sample है we can handle it in t-test. 2 से ज़्यादा sample हो गया तो we cannot do 1 t-test, we will have to do ANOVA. Make sense? Okay. Now, अभी चलते हैं Python पे.
सर ये दिस इज द वन वे ANOVA और 2-way ANOVA, क्योंकि ANOVA is 2 type, right?
अभी आप ANOVA समझो. 1 way 2 way. This is actually a 1 way ANOVA, but बाकी सब के लिए ANOVA. ठीक है? सिर्फ ANOVA. 1 way 2 way पे मत जाओ. Okay? नहीं, डेटा को अलग अलग कर लिया था ना. हाँ. नहीं दिया था ना. हाँ, मेल यूजेज का कॉलम दिया था, फीमेल यूजेज का कॉलम दिया था. अभी दिखाते हैं. ये देखो आप, मेल स्पेंड, फीमेल स्पेंड. नहीं कॉलम ये यहाँ पे देखो. Now, next test is ANOVA. To test for ANOVA, what you need to do is separate out data for each segment, right? So the first thing that we do is we separate out the latest month usage as per the segment. So I have S1, S2, S3, 3 segments. Then what you do is from the stats, scipy.stats, you use F one way. One way stands for one way ANOVA, but abhi ke liye doesn't matter. ANOVA, okay? F underscore one way, and within that you pass on S1, S2, S3, or if you have more than 3, pass them on separated by commas, right? If you had 4 population, comma S4. Make sense? Okay.
Sir,
as soon as
I guess I missed something. Like what are the segments?
sorry.
What are the segments? Like what are the segments means 1, 2, 3? Yeah.
Segment just mean what is the type of credit card you are using. 1 stands for, let's assume 1 stands for gold, 2 stands for platinum, 3 stands for silver.
Got you. And ANOVA, you said when we are going to have ANOVA?
ANOVA is used if you have a scenario like this, where you have more than 2 samples which you want to compare their mean for, right? Then you use ANOVA.
Okay. Okay.
Yes. Now, if you run this, what you get is again two things. You get a statistic and you get a p-value. In ANOVA, we are only interested in the p-value. Statistic does not matter. Basis the p-value, what is your conclusion? What is the business conclusion?
That
What is the
all the
business
three mean are
conclusion?
same.
The business conclusion is all segments are not the same. Isn't it? Okay. Now, why do we call it F one way? The reason we call it F one way is in ANOVA, the test statistic that you calculate, which you will see in linear regression, follows a F distribution. When we do linear regression, you will clearly understand why F. You will see in the numerator you have a square of normal, in the denominator also there is a square of normal. Okay. हाँ सर पहले आप ये बताओ p वैल्यू के ग्रेटर देन 5% है p वैल्यू आप एक बात समझो एक तो p कभी 7.3 हो नहीं सकता है ये प्रोबेबिलिटी है तो 7.3 यहाँ पे लिखा है मतलब कुछ तो पीछे लिखा हुआ है ना 7 तो कभी हो ही नहीं सकता है प्रोबेबिलिटी ओके
So p value here is less than 5%, right?
exactly so you
So
reject
that is why we'll reject the null hypothesis.
Correct. What was the null? That the means were equal. So you say at least one of the means are not equal. Okay. So I will stop here. But what we will do is I'll give you an exercise to work on. So today you will get this basic statistics exercise. Not all of them you will be able to do because we have not looked at all these scenarios, but you should be able to do most. Okay. Now, read the first problem and tell me what test you will do. Paired, right? It's paired sample t-test because for the same patients you are looking at before the diet, after the diet. Right? But two paired sample t-test, one for weight, second for triglyceride. Right? If any of them gets rejected, you will say the diet has worked. You understand, right? Diet, even if the diet does not reduce the weight, if it reduces the triglyceride, then also it's worked. Right? So two paired sample t-test, if any of the t-test gets rejected, you will say the diet has worked. All of you agree with this? हाँ पेयर्ड बोल रहा हूँ ना मैं हाँ बट टू एक वेट के लिए दूसरा ट्राइग्लिसराइड के लिए दो अलग अलग वेरिएबल्स है ना
सर कैसे पाइथन कोड में दो कैसे लिखे दो पेयर
दो अलग अलग फंक्शंस लिखोगे आप
अच्छा अलग अलग लिखेंगे ओके
हाँ एक ही बारी में नहीं होगा ओके नेक्स्ट कौन सा टेस्ट होगा टू सैंपल टी टेस्ट आधे को मिला आधे को नहीं मिला ना तो अलग अलग सैंपल हो गया टू सैंपल टी टेस्ट ठीक है बाकी यू विल हैव टू अंडरस्टैंड ठीक है दोनों हमने किया है ना बाकी यू विल हैव टू रीड एंड अंडरस्टैंड ठीक है okay so you will get this again not all of them you will be able to do I don't think you will anyways do it today so by tomorrow we'll cover everything so then you can start okay cool so I will stop here today and we'll continue from